A woodpecker slams its head into a hard object about 80 million times in its lifetime and doesn't suffer from traumatic brain injury. Why? Well, that was a question that was posed at a DARPA, or Defense Advanced Research Projects Agency event a number of years ago. Those in attendance laughed at the question. Well, everyone but Dr. David Smith, an internist who started to look into why woodpeckers can endure repeated jarring of their skulls and brains. He learned the mechanisms in their skull, shoulders, and the way in which a woodpecker's tongue is attached to their skull and then attaches to the omohyoid plays an important role in reducing TBIs. It appears their physical makeup and the interaction between them combines to trap blood and cranial fluid inside the skull, preventing or reducing brain slosh. Smith wondered if the same could be true for people. So he ran experiments on humans that demonstrated that pinching the omohyoid pinches the jugular and increases the volume of fluid in the skull, preventing brain slosh. So that was part one of the non-traumatic equation. Part two involves CO2, a gas that Dr. Smith said is vitally important in preventing and healing traumatic brain injury. Smith says CO2 is his favorite gas. He once again turned to the woodpecker, which lives inside a small cavity in a tree where CO2 levels are at about 5%. His research led him to study other animals that ram their heads into objects and one another, like giraffes and bighorn sheep. And once again, their exposure to CO2 levels was high, some by where they live and others by CO2 manipulation. We invited Dr. Smith to join us for a conversation that matters about his research in reducing and healing traumatic brain injury.
Conversations That Matter is a partner program of the Center for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the following and viewers like you. Please become a patron at conversationsthatmatter.tv.
Dr. David Smith, welcome to Conversations That Matter. You're coming to us online from Cincinnati, where you have spent a good portion of your career looking at a wide variety of different innovations in medical science. One of them, of course, is the relationship between CO2 and traumatic brain injury. What led you to start to go down this path?
Well, at one facet of my life, I actually owned a wound care company. And in that facet, I was standing in front of the Army Research Lab, showing them one way that we may not bleed out on the battlefield. And when I was done, one of the gentlemen walked up, put his arm around me and said, "Gosh, that was really clever, Doc. You know, how in the world do we get somebody that's clever to figure out traumatic brain injury?" And I immediately laughed and chuckled, and the guy in the front row said, "I think if somebody could just figure out how a woodpecker can smack its head into a tree 80 million times in its lifespan, wouldn't we have all of this figured out?"
You and I talked off camera before, and you told me that there's something very interesting about the anatomy of a woodpecker's skull that helps them to ensure that their skull stays full at the moment of impact. Because you just mentioned that they ram their head against some hard object about 80 million times in the course of their lifetime, and yet they're not suffering from a traumatic brain injury. So CO2 is one component, and that's the part that I want to get to. But I was fascinated to hear, first of all, how they cut down on brain slosh.
Right. Well, we actually identified two different mechanisms. Nature is like that. It's very, very rare to find that there's only one pathway that nature will choose. There's usually an accessory pathway as well. The one that also has led to quite a bit of research on our part is the fact that this creature has a very strange omohyoid apparatus.
Which is, what's that? What is an omohyoid?
Yeah, it's the tongue apparatus for the woodpecker. And if you look it up, you'll be stunned at the anatomy, in that it attaches literally to the top of the beak and goes up between the eyeballs on the outside of the skull underneath the scalp, and then actually comes back underneath and then reattaches and goes in and out with every impact. And when I first started looking into this, there were over 500,000 Google hits on why this animal's anatomy looks that way. Well, I am not one to necessarily go with conventional wisdom, and with a background in physics and chemistry, as well as internal medicine and we'll call it detective work, I came to conclude that what these animals were doing was compressing the jugular vein with each movement of the head. That compression of the jugular vein is identical to what happens in us humans when we yawn. So, approximately 6 to 7 years ago, the medical literature for humans also identified that yawning creates a rise in intracranial volume, and that, in my mind, would be similar to what an airbag does when it goes off in your vehicle. Suddenly, all the different tissues are able to accelerate and decelerate at the same rate, no matter what their density is, and that would prevent shear and strain and trauma and tearing. So that was what we presumed to be the case, and we set out to actually try to prove that and demonstrate that in a number of different ways.
So let me understand. When a woodpecker drives its beak forward, it's in essence, I guess, is pulling its tongue through its throat, pinching the jugular, and then locking the blood and fluid in its skull so that there isn't going to be brain slosh.
Oh, correct. I could probably define it a little bit more accurately, only in that the muscles in the back of its shoulders are massive. That's been well described in the literature, and it's been described as a shock absorber, and I just disagree. What they do is they hold on to these omohyoids, which are attached to the actual jugular vein in humans, and when they hold on to them like the reins of a horse, the head moves forward and it literally compresses the jugular. We've been able to demonstrate in humans that, in fact, yawning does compress both of your jugulars. Strangely enough, at least in the United States, woodpeckers are endangered species. I was not able to purchase one. I'm not allowed to experiment on one. But strangely enough, we are allowed to experiment on humans. And so ultrasounds and all types of evaluations have now been done. There's probably close to 50 different publications that have demonstrated the physiology of a yawn has no gas movement. When you raise your arms up over your head, you pendiculate and your shoulder blades turn inward, which is where the omo comes from. Omo stands for shoulder in Greek. And so your omohyoids are pulled straight back, your jugulars collapse, and the volume fills up in your cranial space very, very rapidly. And the amount of space inside a woodpecker skull is significantly less than what it is in us humans. And so the amount of filling takes just a very fraction of a second.
Right.
In humans, when we compress our jugulars, it takes nearly a half a second to fill what's called the compensatory reserve volume. It's that kind of excess room, if you will, that is found within the cranial space. When we stand up, blood tries to sift back down out of the cranial space, leaving a potential space or room.
And that's where we're at risk when there's a sudden change in movement. It doesn't even have to be a severe impact. There's a sudden change in movement that can force the brain to slosh against the inside of the skull.
Right. You may recall what are called Newton cradle balls. It's the old steel balls that are descended down from little twine. And when you take one ball out one direction and release it, it comes crashing into the other four balls. Well, the energy of that impact goes through the middle balls and comes flying out the other side. Well, boy, if somebody was going to hit me with a baseball bat, that's exactly what I would want to happen. I would want that impact force to pass right on through and out the other side. Well, in essence, if you can control the movement of the molecules inside the cranial space, then you will in fact reduce the absorption of energy into your brain space. So using that same Newton cradle ball, if I were to take that middle ball out and replace it with a soft, gushy, watery grape, all the energy of the impact will enter into the grape explodes. And the word slosh comes actually from NASA. NASA coined the phrase right out of one of the earliest chapters of any physics book, which is called hydrodynamics, which is the study of fluids inside moving containers. And every time NASA would send up another rocket into outer space prior to 1950, the fluid would dissipate out of the rocket engine's fuel tanks, and then the fluid would start to slosh, and the energy would be reabsorbed from those massive engines, and a catastrophic explosion ensued. And then they finally developed what are called solid rocket fuel boosters, and they've not really had that anymore.
Huh. But they weren't thinking about the brain when they coined that phrase.
Well, I stole it from them in that I've coined it brain slosh. And we now believe that most of the traumatic brain injury does acknowledge that the cause of brain injury is brain movement within the cranial space.
Okay, so you learned that a woodpecker can mitigate the amount of movement of their brain within their skull by this rather interesting and complex physical interplay inside their body. And you say that we can do it if we raise our arms and yawn. Well, at the moment of impact, especially if you're involved in a sport or something like that, you don't have the opportunity to be yawning and raising your arms. Do we have the ability to do this on our own, or does it require some kind of intervention?
Well, that comes into what we phrase as biomimicry. So, if we can figure out how nature's done something, then quite frequently, if we're clever, we can actually find a way to actually mimic or cause the same physiological action. What we were most concerned with when we started down this pathway is that there are counter-regulatory mechanisms of the body, such that if we put a collaring device or a way to cause jugular compression, and then leave it on, that at some point in time the body would, by way of homeostasis, try to go back to the old position it was in. But in reality, we started to notice that in studies of people lying down at night, the pressure inside their eyeballs and inside their brain, it goes up when you lie down, and it stays up for the entire 8 hours that you're lying there asleep. So obviously the body's allowing that rise in pressure to occur. It's not resetting the pressure and volume in your cranial space. And so it was felt that there was such a small decline, or excuse me, a small increase in the volume that it stayed within the physiological norms of the body, and therefore it didn't trigger any of these counter-regulatory mechanisms. So we were encouraged in the very early stages that what we were about to do would not only be safe, but would likely last for hours.
So you've developed a collar that's still very early in its introduction into the market. I understand it's available here in Canada, called the Q collar. How exactly does that work? Because it really is about biomimicry, as I understand.
That's correct. So we're going to get back into columns of fluid. And if you look on the back of your hand and you see a vein on the back of your hand, if you reach down and compress that vein, the amount of pressure that's involved is about 30 millimeters of mercury. And that's counteracting a column of fluid from the top of your head all the way down your neck, all the way down your shoulder, out onto the back of that hand vein. Now, in your jugular vein, that column of fluid is beneath your jugulars, and therefore the amount of pressure that's actually keeping your jugulars distended is only 3 millimeters of mercury. So it's 1/10 of the amount of pressure that we're applying to the back of your hand vein is all we need to apply to the neck itself. And interestingly enough, there's that cool muscle that mankind had no idea why it was in our necks. So prior to our work and prior to the knowledge that yawning leads to a compression of the jugular vein, nobody even knew why we yawned. And so now with this newfound knowledge, we not only are able to realize that physiology, but we're able to take advantage of it and feel that it would be completely safe because the body is built to compress those jugular veins.
From here, based on the amount of time that we have, I want to start talking about the role that CO2 plays in ensuring that if there is any kind of damage, that has a beneficial effect in recovery.
CO2 is dramatically protective towards brain injury as well. We were able to demonstrate that here at University of Cincinnati, whereby we just exposed the little animals to just 5% carbon dioxide level for a very short period of time, and then subjected them to the same kinds of forces that occur to our soldiers on battlefields. And we had a 65% reduction in brain injury just from letting them expose themselves to small amounts of CO2.
This is contrary to some of the research that I've done that says, no, an increase in CO2 is not necessarily beneficial to your brain. It makes you become sleepy, hypoxic, and so on. And yet you're saying that there is a benefit, especially when it comes to traumatic brain injury. How does that work?
Well, everything's a matter of degree. You have to understand that absolutely every cell in your body and every animal cell on this planet Earth all produces carbon dioxide. Carbon
Yes.
dioxide is not toxic in any way, shape, or form. If you want to cast aspersions, it's an asphyxiant, which just means that it's able to push other gases away. So that if you breathe into a paper bag on a regular basis, you're going to extract out all of the oxygen out of that paper bag. And yes, you will be harmed by the lack of oxygen, but you're not harmed by the elevated carbon dioxide. Now, there will be negative effects at very high levels of carbon dioxide, and we have in the medical world hundreds of illustrations of carbon dioxide level going to 20, 30, 40, 50%. But none of that harms the individual as long as the individual has oxygen to their brain as well. So in our other mimicking scenarios, we know that giraffes rebreathe their own tracheal gas, that big long trachea. Their lungs aren't big enough to expel all of that gas out 2 floors up and out a chimney. And so when they rebreathe, they breathe as much as 8% CO2.
Yeah, is there a benefit to the giraffe in doing that?
Well, people don't realize, but the most defensive mechanism that a giraffe utilizes is they headbutt. So they headbutt to 500 Gs, and you and I are thought to have a traumatic brain injury with one hit of 100 Gs typically. But these giraffes do this on a regular basis, not only to vie for mates, but they do it to fight off a lioness that might be looking for a meal. In fact, there was actually a director, a Hollywood type director in Africa just 2 years ago that on stage was struck by a giraffe who headbutted him and killed him instantly. So the forces that are involved are quite voracious and vociferous. And in the same breath, I would tell you, head ramming sheep, they also have very high carbon dioxide levels. So you and I as a human have a partial pressure of CO2 of around 37. Well, head ramming sheep have 47 partial pressure in millimeters of mercury, and a giraffe is way up at 57. And these are massive changes, and yet they're all mammals, just like you and I. So we had to try to figure out whether there was a reason why nature wanted these animals to modulate and elevate their CO2. And it became clear to somebody like myself, who has been a physician for 30 years and a physiologist, that CO2 is the #1 determinant of intracranial volume and pressure. So it determines the rate of flow of blood to your cranial space. So it became obvious to me that that CO2 level may be having great benefits as opposed to any particular risk.
So you're addressing this. You've created a device that helps to elevate the volume or concentration of CO2 that in essence, you're rebreathing the same way that a giraffe might. Tell me a little bit about your device.
Well, the medical literature is very clear for the last 50 or 60 years that very small amounts of delivered carbon dioxide by way of a canister has really cool medical benefits. And interestingly enough, most of those articles talk about how silly it is to carry around a 180-pound canister of carbon dioxide around with you. Well, why not just rebreathe the CO2 that you are exhaling? So we as humans exhale on average about 4% CO2. That's about 100 times the ambient level of CO2, which is 0.04%.
Yes.
And
right.
so this sounds like a lot, but in reality, you really can't feel much change at all in your world when your carbon dioxide percentage is under 6%. When you get up over 6%, you can get a little bit of a headache, you can be a little bit nervous and things of that nature. But once again, it's not harmful, it's just noticeable.
Okay, I'm going to run out of time here, but there's one other thing that I want to touch on that you told me, and it was about the role that CO2 plays in helping your blood understand where it's supposed to deliver oxygen. Because we breathe it in, the blood cells grab it, but how does it know where to release that oxygen in your body?
Oh, precisely. And we medically call that the Bohr-Haldane effect. And the hemoglobin molecule, one of my favorite molecules on the planet, it's not an intelligent molecule. It can't pass through the lung and actually look up at an arterial wall and say, I think that looks like a lung artery. It doesn't know it's in the lung at that point. So how does it know to reach and grab and hold on to oxygen only then to go downstream and then be in a brain artery and suddenly go, I think it's time to release that oxygen. Well, it's called allostery, and it has to do with the fact that there are these massive protein globulins that change their conformation in the setting of carbon dioxide. So envision the hemoglobin molecule as a big catcher's mitt, and it opens up when there's not very much carbon dioxide around, which happens in your lungs. But then when it goes up towards your brain, that high level of CO2 in the brain and in your muscles creates a mitt that closes and literally spits the oxygen molecule off. So that's how the body knows when to hold on to oxygen in one part of the body, being the lungs, yet release it in the brain. And when you go to altitude, we've surmised, and for decades upon decades, that without a reasonable level of CO2 in your body, your hemoglobin molecule, it may have an oxygen on it, but it doesn't know to release it into your brain, and it still suffocates the brain.
So, David, I know that there is so much more to discuss around this, but I'm going to run out of time here. Is there a website that somebody can say, well, hang on a second, a lot of what you're telling me is different than what I thought I knew. Where can I go to find out more information?
Well, we are a development company, and we have a website called DeltaChase.com, and we have started to put a lot of our publications in there as well. The Q-Collar has its own website in Canada, and that's called qcollar.ca. And that physiology is described in part anyways on those websites, but that would be your first best bet.
We've only just touched on these topics, and so I hope that people will go and visit your website to learn more. I've been fascinated by this ever since you reached out to me. I did a bunch of research, and I'm thinking, wow, this goes in some ways contrary to what I thought I knew about CO2 and the impact that it would have on us if there was an increase in elevation of it in the atmosphere. And you're telling me it's not a bad thing.
Yes, we've already identified a number of silos, if you will. We're at about 13 so far, disease states that have been orphaned. Nobody knows why they're happening, and nobody has any clue what to do about them. And we believe we've made inroads on rather dramatic improvements in those, and we're very much looking forward to others coming forward.
Great. Thank you very much.